Alright, so last time we focused on ionic compounds, and we talked a lot about them, and now we're going to talk about covalent compounds. So remember, in an ionic compound, the electrons were transferred, and in the covalent compound, the electrons are actually going to be shared. So in a covalent bond, one atom shares one or more pairs. So they always share in pairs. They'll either share 2 or 4 or 6 electrons with another atom so that both then have a full octet. Covalent bonds occur between nonmetals because nonmetals are all looking to gain electrons. So when they get together, there's no one to take the electrons from. Instead, they will all share because they're all looking to gain. This continuum kind of shows us that scientists have created these distinctions between covalent and ionic, but really it's this continuum. So, for example, if two atoms have an electronegativity of 1.9, they are right on the line between covalent and ionic. But in reality, they probably have characteristics of both. So as the electronegativity difference between two atoms gets bigger, the bond becomes more and more ionic. And we just chose this arbitrary number to say at 1.9, that's where we're going to say it's ionic, because we need a way to organize. But it probably has properties of covalent there too. And before 1.9, those are going to be polar covalent, which means that the electrons are not equally shared, but they are shared. And then on down the line, if we get a really small difference, like the difference between them is only 0.5 or less, we'll call those nonpolar. Although at 0.5, they probably are acting a little bit polar, but that's just where we put the cutoff. So less than 0.5, we'll call those nonpolar, and that's going to mean that their electrons are pretty much equally shared. So for nonpolar, try to text in some stuff here. Okay, for nonpolar, we have equally shared electrons. For polar, those electrons are going to be shared, but unequally. One of the atoms in the pair is going to kind of hog the electrons, but they'll still be between them for the most part. And in the ionic bond, electrons are transferred. So they are definitely not shared in an ionic bond. So you see in the continuum, we have equally shared, unequally shared, and then transferred. But somewhere in there, they're like kind of equally, but not too equal. You see how it's continuum. Okay, but we're just going to create these cutoffs to help us distinguish. So just looking at some examples, maybe this will be more clear. So fluorine and fluorine. If we look at those two atoms, neither one of them is more electronegative than the other. They're both fluorine. So they're going to share their electrons evenly. So you can see in the picture that the electron cloud, that's what's being shown here, is evenly distributed around those two fluorines. However, a hydrogen in the fluorine is much more electronegative than hydrogen, so the electron cloud is going to be distorted so that it's more over toward fluorine than hydrogen. So that's what a picture you can kind of see of a polar covalent bond would look like. The coloring here is kind of like a weather map. So this green is showing you lots of electrons, whereas the blue is where we're not seeing many electrons. We call this electron poor, and then electron rich. We would also use symbols. See if I can get my little pencil again. So we use this S to mean partial. So this is like partially negative over here and partially positive on the hydrogen. Okay, because the fluorine has the concentration of the electron. Sodium fluoride, however, is an example of an ionic compound. It's not just that the electrons favor the fluorine, so they spend more time around the fluorine. It's actually that fluorine took sodium's electrons. So in HF, which is what we looked at for polar covalent, fluorine is still kind of sharing with hydrogen, but in NaF, fluorine takes the electron from sodium. That's what makes this ionic and this covalent. Here they're still sharing. Here, not sharing. Okay, so how do you tell if it's going to be ionic or covalent? Just stick with two nonmetals. That's going to be covalent. A metal and a nonmetal is going to be ionic. But it's based on their electronegativity differences. So we could go back last chapter and look at that chart. When you subtract those values, if it's more than, what did we say on the last slide? If it's more than 1.9, then that's going to be ionic. All right, what does polar covalent mean? Okay, so this slide goes through a good explanation of that. The atom with the higher electronegativity develops a partial negative charge because the valence electrons from both atoms spend more time around it. The valence electrons from both atoms spend more time around it, and it is the atom with the higher electronegativity. So in HF, fluorine had the higher electronegativity. So both of their valence electrons spent more time around fluorine, and that gave fluorine a partial negative. We call it partial because fluorine didn't take the electrons away completely, so it's not a full charge. It's a partial charge. The atom with the lower electronegativity develops a partial positive charge, which is equal in magnitude to the partial negative charge. So they add up to 0. If this one has a partial negative of, negative 1.7, then this is a positive 1.7. Okay, that's just a random number, but they're equal in magnitude. As the electronegativity increases, the difference between them, as it increases, that partial charge is going to increase as well. And it almost becomes close to a full charge. Okay, so when I said a partial charge of 1.7, that was kind of inaccurate because a partial charge would be less than 1. But as the electronegativity difference grows, that partial charge is going to be closer and closer to a real charge, and then once it gets to be ionic, it is a real charge. Okay, so let's look at some examples of determining bond type. Hydrogen and hydrogen. Well, they're showing the electronegativity values here, 2.1 and 2.1, but duh, it's two hydrogens. Of course they're going to share equally. Which hydrogen is going to hog the electron, right? Neither one of them. So anytime you have two atoms that are the same kind, F, Cl, Cl, bonded together, bonded to themselves, essentially, that's going to be a nonpolar covalent bond. CH is an important one to know. C and H, their electronegativity difference is less than 0.5. So C and H is considered to be nonpolar. So this bond is really popular. We'll see this bond a lot. That is considered to be a nonpolar covalent bond because their electronegativity difference is less than 0.5. HBr, on the other hand, if you think about bromine, is all the way over there by fluorine, and those have high electronegativity values, and then hydrogen all the way over here on the left, the difference between their electronegativity is 0.7. That's greater than 0.5, so that would be polar covalent. Now, which element is going to hog the electrons? Well, bromine will, because it has a higher electronegativity value. So bromine is going to have a partial negative charge, while hydrogen has a partial positive. And that makes this molecule polar. Right? What about carbon and oxygen? So in this bond, oxygen has an electronegativity of 3.5, is right there by fluorine, and then carbon's electronegativity value is 2.5. That's a difference of 1. That's greater than 0.5, but it's not all the way up at 1.9, so that falls under polar covalent. Which of these two atoms hogs the electrons? Well, oxygen does, because it has a higher electronegativity value. So it would have more electrons partially negative, while carbon would be partially positive. This oxygen over here also trying to hog the electrons, partially negative, compared to carbon's partially positive. Right? In lithium fluoride, lithium a metal all the way to the left, fluoride a nonmetal over there on the right, they have a difference of 3. That's much greater than 1.9. So that's ionic. But we know that already. So don't get caught up in the numbers. Lithium's a metal, fluoride's a nonmetal, ionic bond. the electrons are actually transferred. So it's not that fluorine is partially negative. Fluorine is negative. Lithium is positive. All right, so covalent compounds. All right, covalent compounds are also known as molecular compounds. And this is when two or more nonmetals bond together to form a compound. Nonmetal, nonmetal, nonmetal. These could be nonpolar bonds or polar bonds. So they're sharing their electrons, but they may not share evenly polar, or they may share evenly nonpolar. If some nonmetals get together and they form a bond, but together they have a charge, that charged group is a polyatomic ion. Okay? For example, carbon and 3 oxygens. If one carbon and 3 oxygens get together, so let's say that's CO3, and all together they have a charge of -2, well, that is a polyatomic ion. Okay? A polyatomic ion is a group or combination of nonmetals. Sometimes there's a metal thrown in there. And when they bond together and have a charge, they form a polyatomic ion. Inside this polyatomic ion, you can have nonpolar covalent or polar covalent bonds. Inside the polyatomic ion. Then the polyatomic ion can join with something to form an ionic bond, but inside the compound, there are also covalent bonds. All right, Lewis structures. Hopefully you know something about these from pre-AP or from regular chemistry. These structures, we're only going to draw these for covalent compounds, what we're going to call molecules. And these structures provide a visual representation of where the atoms are and the distribution of the electrons within the grouping of atoms. So we have to know how to do Lewis structures for a variety of reasons. One reason is we have to know how to do Lewis structures if we're going to predict the shape of molecules. And the other reason is we have to know how to do Lewis structures to tell if something is polar or nonpolar. The first step in a Lewis structure is to figure out the number of valence electrons in the molecule. So if we start off with PCl3 as an example, P has 5 valence electrons, while each chlorine has 7. So 5 plus 7 times 3, in this molecule there are 26 valence electrons. Now, why do we care about valence electrons? These are the only electrons involved in bonding. Only electrons involved in bonding. Okay, very important. So only the valence electrons are we worried about here. All right, the next thing we're going to do is to put the least electronegative atom in the center. Okay, that's an important step when we're drawing the skeleton structure. Put the least electronegative element in the center, and then connect your other atoms to it with single bonds. Here they're showing 2 electrons, but that is the same thing as a bond. Okay, you wouldn't draw both, but if you draw a single line, a bond, so you could just draw it like this. And again, the location of these chlorines isn't important right now. So just 3 chlorines attached. When you draw a line, that single bond, that is 2 electrons. So you could draw it either way. You could draw the 2 dots to show the 2 electrons, or you could draw the line and know that it is 2 electrons. So a single bond equals 2 electrons. Now there is an exception to this rule. Hydrogen is always a terminal atom. That means it's never in the center. All right, the next step is to complete the octets. Okay, we know that octet means 8. For all your terminal atoms except for hydrogen. So you look at your outside atoms and you give them all 8 electrons. So this chlorine already had these 2 that it was sharing with phosphorus. So we put 6 more around it. That's 8. This chlorine had these 2 that it was sharing with phosphorus, so it needed 6 more. And this chlorine had these 2, so it needed 6 more. So each of the chlorines now has 8, and those are our terminal atoms. We haven't messed with our center atom yet. Right? Then you add up the electrons you have used and subtract them from the total valence from step 1. So in step 1, we found that we had 26 valence. So far, we've put 6, 8 on each chlorine. So we've used a total of 24. So we have 2 left. Anything left over goes on the center atom as a lone pair. Any leftover goes on the center atom as a lone pair. Alright? So that is an example for PCl3. Again, these 2 dots that you see could be lines. Okay, either way, I will most often do it as a line, and you'll see them using the 2 dots. And then you've got your dots around your chlorines and your 2 dots on your phosphorus. All right, let's look at another example in carbon dioxide. So first we're going to count the total number of valence electrons in the molecule. Carbon has 4 valence electrons, while each oxygen has 6. So 6 times 2 is 12 for the oxygen, and then 4 from the carbon. So we have 16 total valence. All right, our least electronegative is carbon. It's the furthest away from fluorine, so we're going to put it in the center, and then connect those oxygen atoms with single bonds, or 2 electrons. We'll then complete the octets for the terminal atoms, except for hydrogen. So we're going to give each of those oxygens 6 more, so they have a total of 8. All right, we'll add up the electrons that we have used. So we've done 8 on each side, so it's a total of 16. Now we're going to subtract those from the valence we started with. If we look back to step 1, we said we had 16 valence. So 16 minus the 16 we've used, we have no electrons left. It says to attach the leftovers as lone pairs, but we don't have any left. Okay, so here we are kind of stuck. We do not have extra electrons, and carbon's octet is not full. So what are we going to do? We're going to go on to step 5, which we haven't seen yet. In step 5, you make multiple bonds, that could be a double or a triple bond, to complete the octet of the center atom. Okay, so how is that done? We're going to borrow, carbon actually needs 4 more electrons. So we're going to borrow 2 from each of these oxygens. And when we borrow them, we put them between the 2. Okay, so like these 2 electrons from this oxygen are going to go between here. So now they can share them. Okay, so they're not down here anymore. And these 2 are going to go between here as well, so that they can share them. So you can see now how each element has 8. So this oxygen still has 8 around it. Those are just between it and carbon now, where they're sharing. And this oxygen has 8 around it. And then if we switch to a different color and we'll circle with purple, you can see this carbon has 8 around it. Okay, so how do we show that we move those electrons in? A better way to draw this would be, as you see here, showing a double bond. So a double bond would mean that 4 electrons were being shared instead of just 2. So this is the correct Lewis structure for carbon dioxide. Notice the electrons that were down there under the oxygens are missing because those were moved in to make that double bond. Right, in some cases, you'll have to make triple bonds to complete the octet, and so a triple bond represents 6 shared electrons. And you can see there in HCN that we needed a triple bond between carbon and nitrogen to fill up carbon's octet. If you're making a Lewis structure and something has a charge, such as a polyatomic ion, you're going to take the overall charge into consideration when you count your electrons. Okay, so on this one, when they were counting the valence, iodine has 7 valence, then each oxygen has 6, so 6 times 3, and then that -1 charge. -1 means you gained an electron, so they added 1 to the total, So for the total, they had 26 electrons. You also want to show that charge when you draw the Lewis structure. So once you finish the Lewis structure, you put it in brackets, as you see they did, and then you write the charge on the outside. Because that charge belongs to the whole compound, not just one element in particular. If this was a positive charge, then you would subtract electrons from your total, because a positive charge means that you lost some electrons.